Thank you very much for the kind introduction. I'm very sorry. It's a torture for you to pronounce French name. I get that. That's fine. And you did a great job, actually. So thank you very much. So, good morning, everybody. I think this is the last day. You might all be very exhausted. So don't worry. Today it will be very practical. I won't throw at you too much equations. Just fasten your seatbelt, sit, enjoy. That's not going to be difficult. Okay. We'll talk actually about something rather applicative. This is visual localization. I will try to give a sort of overview of the different strategy we can use. And at the end of this talk, I hope that if one day you need to address a similar kind of problem, you will be like, okay, I know what to use, what tool to deploy. And for further details, then you just need to dig a bit in the literature. We'll talk about old stuff, more recent things. So it's quite a broad overview, you will see. So the topic we'll talk about is visual localization. And to illustrate that, do you know what is GeoGuessr? Do you guys have ever played GeoGuessr, or do you know what is GeoGuessr? Yeah? So can you explain what it is to others?
It's a game that shows you pictures of random countries, and you have to guess which country and which locality it is.
Exactly. So basically, you have a random picture. It says that's a very good one. Actually, you describe what is visual localization. You did my job. So you have a picture, and then the user has to pinpoint the geographic location where he thinks this picture has been located. Okay, how do you think we can do that? I mean, as a human, we look at the image and we're like, hey, this picture is from Nepal, for instance. What could make you think a picture is acquired in Nepal? You might have some clue. You might see the language. You might, maybe those kind of grass is growing in Nepal. You know it, and this is embedded somewhere in your brain. And sometimes the clue you use to localize yourself to know that this picture is from Korea, this picture is from there. We cannot always really say oh, this is because this or that. This is just an overall feeling. Now, so sometimes it's a clear landmark, sometimes it's not. It can be a texture, it can be anything, And even those GeoGuessr players, but it's quite funny. I don't know if we talk a lot about that in this school, actually. They will take advantage of certain aberration of the image, certain how to say, glitch, or they know that a certain car appears in Australia, so they will guess. So they use also some, I will say, they are cheating a little bit, and your neural network will do the same thing. Actually, that's funny to see. We take the same shortcut. Anyway, I'm drifting too much away here, but yeah, basically, visual localization is the idea of how we basically localize ourselves, using a picture. Okay, so it's a bit like a GPS, but using images in some ways, right? Okay, what I wanted to add to that. So yeah, before we dig further into the technical details of that, I want to interrupt this presentation briefly for a short commercial break. Okay, that my university tells me you have to do that. Okay, and people are curious actually. So because I'm a kind of weird guy, I have 3 hats. One in NAMI, and that's one of the reasons I'm here today. I could collaborate with fantastic people here in Nepal. But most of the time, I'm actually located in Korea. But I'm actually working for an American university, which is located in New York State. This is Stony Brook University in Long Island. Okay? But we are basically just a branch of Stony Brook, and we're called SUNY Korea. So basically, we offer exactly the same kind of program as the student will receive in the US. But located in Korea, if you guys don't want to be in US, basically. So we offer the same diploma. Everything is the same, actually. Just the location is different. And then the feeling is different. The students are different as well. And all our students are required just to spend 1 year in the States. Okay, that's so this is a different experience that they can get. We are opening now. So we also offer PhD and master program. And we open a new master degree about data science. So if you guys are looking for a master degree, you can type SUNY Korea, you can contact me, whatever, okay? So feel free to do that. Now let's go back to visual localization. Before we start talking about that again, I was talking with some research assistant in NAMI, and I have to confess something about this. I think I know exactly how to resolve this problem, how to localize a camera in space, at a centimetric level using a computer. But after 2 weeks in Nepal, I realized that as a human being, I'm the worst visual localizer ever, okay? So trust me in the technical things, but if you follow me in Kathmandu, don't trust me. So we have seen like a rough definition of what is visual localization with, like using this, image of GeoGuessr somehow. Like, let's try now to see a more formal definition of what is visual localization. So visual localization is the problem of estimating 6 degrees of freedom of a camera pose, which a given image was captured relative to a reference scene, representation. I think I lost my pointer, never mind. I don't know where I put it. It's okay. Yeah. So basically, what we want is more than just, a rough approximation of where the picture has been acquired, like in GeoGuessr. Oh, yeah, the pointer is here. Can you, sorry. Thank you very much. So we want more than just a rough, approximation of where the camera is located. We really want to know exactly where the camera is in space, and we want to know. It's okay. It's on. Yeah. We want to know exactly where it is, and like always, we start with like a representation of the environment. So basically, a map. It can be any sort of map. Here, the example is a 3D point cloud, but really it can be anything. We'll see more example later. And then if I give you this query image, the question is like, where is this image being captured? And we want to know basically exactly where it is. So we talk about 6 degrees of freedom. What are those 6 degrees of freedom? Rotation and translation, right? Because here we work in a 3D space. It's not always like this. It depends like in what environment you want to localize yourself. But in general, this is what we want. Indeed, like you want to know like 3 degree of freedom in translation, X, Y, Z in the 3D space. And you want to know where you're looking at with this camera, so it's basically 3 additional degrees of freedom for the rotation. You can think in terms of your angle, like you have 1 rotation around each axis. Rho, pitch, yaw, somehow. And then it will tell you precisely where this picture has been acquired in the 3D world. So can you guess actually where this thing can be useful? Definitely in 3D reconstruction. In many other stuffs as well, like in autonomous driving, like what you don't see in autonomous driving is like behind the hood of the system, there are like a huge, basically, localization in some HD maps that have been created that basically contain all sort of information about the road environment. And that's totally right, used a lot in 3D reconstruction. So we'll talk later about image retrieval and all those kind of things. And this is something that is at the center of like structure from motion and many other stuffs. I think the first thing that comes into people's mind when we talk about visual localization is like, those Pokemon Go kind of game, or like any actually augmented or virtual reality. Like if you want to place some virtual object in the scene, very often you need to relocalize yourself in that scene, okay? If you guys are doing a little bit of robotic navigation, SLAM, then typically we use those things, to avoid the drift over time of your motion estimation, for instance, okay? It can be used for any mobile localization. Here is an example from some friends in Naver Lab in Korea, where they basically tackle some very challenging problem in a very complex environment. And there are many more than this. I even have a friend, he's trying to localize a camera in your digestive tract. So he's mapping your inside using so that you have to swallow a sort of camera. And then after, for the next operation, you can take another pill somehow, and he tries to localize it inside. So there are many, many things. I don't work with those kind of medical, challenges, thankfully, but there are many applications of visual localization. So you can also use, you can localize yourself in different representations. We are talking about GeoGuessr. What is the representation in GeoGuessr? What is the map in which you localize yourself? In GeoGuessr, it's not a 3D map. In GeoGuessr, you need to pinpoint your location on what? Yeah, it's a map, right? This is the planet, actually. That's the entire Earth, right? This is a projection of a sphere, in that case, right? So how many degrees of freedom you have to solve is 2 only. The longitude, latitude, right? That's an easy problem. I told you that in general, we will try to go further than this. We'll try to estimate 6. But again, it depends in what kind of representation you want to localize yourself. So one example I gave before is a 3D point cloud, okay? Like this. And in that case, probably you will have to address 6 degrees of freedom. We will see another example that is much more common than just a 3D point cloud. It's basically what we call a structure from motion 3D map. And we'll discover that those kind of representation, they're the most widely used for place localization because they contain very rich informations, okay? And it can be some other stuff, so something quite similar to what we have seen with GeoGuessr. It can be a roadmap, okay? We call those things actually SD map, and they're very interesting paper those days, like coming up with that, okay? It can be a blueprint, it can be a CAD model, it can be anything, you can be creative. Whenever you have like the representation of an environment, whatever it is, then you can think of a new localization problem, basically, okay? And the point of visual localization, of course, is not to use any GPS or, you can eventually have them as additional information, but I would say the main goal is like how we can replace any other sensor just using images. So the most common input you will provide to a visual localization network is basically a basic perspective image from your cell phone. You have no distortion, easy peasy, okay? And in general, we start with those kind of images to make it simple. But there are actually other kind of modalities you can use that will be very beneficial to localize yourself, actually. And one of them that I particularly appreciate is omnidirectional vision. So for instance, instead of giving a simple, narrow field of view image, you can also use those kind of omnidirectional image. And you see that it's actually in general very interesting to use those kind of images. Why? Because you have much more landmarks. You have much more chance to see something that is of interest for your localization. Because if you use a very narrow field of view and you look at the ground, that's very likely you won't be able to really localize yourself, right? So omnidirectional images are interesting. You can get those kind of images using some catadioptic system or multiple cameras, whatever you want, okay? If you want to localize yourself maybe during the night, or you can use thermal camera. You can have some prior information about the depth using stereo system, or you can even use like chunks of videos, and also it will be more rich in information, okay, instead of just using one image. And you can take any modalities you want. You can take even camera, something very exotic if you want, okay? To some extent, some people will assume as well that localizing yourself with LiDAR input will also be considered to some extent to visual localization, even though it's not really an image, but anything that your perceptual sensor will give you will be considered as visual localization input. But it sounds like a simple problem, right? Like I give you an image, you tell me where this image has been located in a given referential, okay? But in reality, this is much more complicated than we think because there are many challenges that occurs when you apply those strategies in a real setup, okay? So one of them that is very obvious is that imagine like you capture your scene originally using, during the daytime, okay? And now you want to localize yourself during the night. Well, now you have a little bit of a problem because those scenes, they don't look alike anymore, right? And then how can you really know that this image in the dark is the same as this one, okay? Even though you see the viewpoint is very close, nonetheless, all the descriptor of that image, they will be widely different. They will be completely shifted, actually. So you want something that is invariant to those photometric transformation. You have other challenges, like, for instance, how you localize yourself in, like, an environment with very low texture. And even for us, human, this is very difficult. It's like, when you're in hospital, like, the corridor, they're always the same. How do you know at what floor you're located? Those kind of things. Like, they're also very, very complicated to deal with. You can also have like some drastic viewpoint difference. Like if I take a picture of this room of you guys from here, or a picture from where Suman is located right behind you, that's what he's doing right now actually, then it's very, like the viewpoint will make the scene look completely different. So that's yet another challenge. The seasons can be different if you want to do long-term localization. Or sometimes you can have occlusion. When you work in a dynamic environment, some of your landmarks might be basically detected on some moving object. And then, well, good luck to localize yourself after that. And another challenge might be the scale, for instance. Imagine you want to localize yourself in a huge city is not the same as if you want to localize yourself in a tiny room, okay? So now so here are the challenges. Now I want to talk a little bit about the metrics because later we'll see different techniques and then we might need actually those things. So the metric is actually rather simple. You want to basically know what is the discrepancy between the translation you have estimated and the ground truth translation, so that's just the L2 distance between them. That's a very typical one when you work in 3D. And for the rotation, that's a bit different. That looks a bit more exotic, but this is actually quite simple. we basically use this formula most of the time, and it will give you a single number that will be a representative of how good your rotation is, okay? Because if you look at this, like rotation matrix, there are some weird animals, they are orthogonal matrices determined on 1, and another specificity of orthogonal matrices is that if you multiply itself with its transpose or its inverse, then this thing should become identity. So if you did a good job at estimating your pose, then it means that this thing here will be an identity matrix. So if you take the trace, you should get 3. 3 minus 1 is 2. You take half of it, it should be 1. R cos of 1 is 0. And you see you have something that somehow will be representing your rotation error. So we use basically this metric when you want to know for one sample how good you have been, in rotation and translation. But when you work like on a large collection of image, we tend to actually use the success rate as a more robust metric. So the success, imagine like you have like a data set that you want to localize 10,000 images, in an environment. Imagine you did a super good job, you're super accurate for almost all the images, but one image is located super far away. You have a huge outlier. So it means that the mean of that will be bad, even though actually your algorithm, your network is good. Okay, so what we do is we just look at the percentage of image that has been well categorized for different level of accuracy in rotation translation. And if you read basically visual localization paper, most of the time we rely on those kind of metric to determine like if we did a good job or not. Okay, so here there are a few examples you cannot see well, but I guess you will have the slide. And then also the community in visual localization is very big, and depending on the challenge you want to tackle, I can guarantee you that you will always find a data set that you can use to basically test and train your strategy. So some of them will have some challenge for day and night, some of them will be some different weather condition, some of them will be indoor, some of them will be like on very large scale, etc. And there are many, many more than this actually, if you want to test your technique. So now, like when you address the problem of visual localization, you can sometimes, depending on the application, you might have different granularity. You might have different, like basically, accuracy that you want to achieve. Okay? And like there are basically 2 levels of accuracy that in general we consider in visual localization. The first one is image retrieval. Okay? So the idea here is you're given a huge data set of images. Let's say you have 10 million images of different places across the world. Okay? And what you want to know is what image in this database is the closest from your query image, basically. Okay? And then if you find an image that looks very similar to your query image, well, you can start from the reasonable assumption that, hey, they have been captured more or less at the same location. Okay? So if you're lucky and you have basically all your image in your database that are geolocalized, you can say, yeah, I'm in Paris here, I'm in front of the Louvre. Okay? Something like this. But of course, it's not very accurate. The real goal of visual localization in general, this is basically to localize yourself in like much more accurately than this. Okay? At a very exact location where the image has been captured. And it's a topic that actually has attracted quite a lot of people for the past 20 years at least. And people came up with different type of strategies. Here is a taxonomy that I really like that has been proposed by some guys in Naval Lab Europe. They're like expert in that field. And here it looks a total mess for you at this point, okay? My goal through this lecture, hopefully, is that at the end of the lecture, you come back to that thing and you go, it makes total sense, okay? I hope, I'm not sure. But we'll cover actually most of those strategies, so it's maybe a bit ambitious. I hope we'll have the time to finish. And, well, hopefully it will be more clear to you later, okay? So before we directly start with visual localization, we need to understand in what we want to localize ourselves. And most of the time, we localize ourselves in a 3D map that has been creating with structure from motion. So I will briefly talk about structure from motion. That's not the core of the lecture, so there will be no details. Just I want you conceptually to understand what is going on when you basically try to make a 3D reconstruction using images. So structure from motion is just how I will say the oldest probably strategy to reconstruct a scene in 3D from a set of images. So you start with images of whatever you want to reconstruct. Maybe you can take many images of that room, and then you can basically feed. So like here, for instance, is the pipeline from CallMap. So CallMap is, if you want to start 3D like what I encourage you to do is you download CallMap and you try to push some image in there, okay? And the way CallMap is working, or any SFM is working, is that first you will extract some local features on your images, all of them. You can have like 10 images, 100 images, 1 million images, doesn't matter. You'll extract some local feature that looks interesting, okay? And you will basically try to match those features across images. So you see there are local features. On the top image here, this is an example of image matching. And you will do it for any possible pairs of images you can have, okay? So here I will say this is the most difficult stage in 3D reconstruction. How to find those correspondings is very difficult, okay? What comes next is basically pure geometry at this point, okay? Like given those pair of images, how I can together find the poses of all my cameras and how I can triangulate all those points to reconstruct the scene, okay? And we do some, you know, like additional refinement, whatever, okay? And you should end up with actually the beautiful 3D reconstruction of the scene, all the poses of your cameras, of all the images you use, etc., etc. So here is somehow how image, like feature matching is working. Imagine you want to find the correspondence between those two images. You can first detect some distinctive points on image one. I'm not sure if you see them very well, but there are little red dots here that appears at some somehow interesting location, something that will be repeatable somehow. You do the same on image 2. Sorry. Okay, you detect a set of key points, and what you can do next is like you will try to extract some meaningful feature in the locality of all those key points. Okay, you extract a little patch, and you can use a neural network or whatever you want to basically have some representative vector for each of those local key points. And now what you can do is you can try to associate them one with another. Okay, this is a bipartite matching somehow. Like, and for instance, you take this first descriptor, you can be like, hey, which one is the most similar to me? Okay, and then you will be like, maybe they're matching. And you will take the next one and you will try to do the same and again and again. Okay, so if you're able to do that, then good job, you are done with image matching somehow. Okay, except that you can have some outlier contamination. You can have many problems that can occur. Okay, so just to come back a little bit to key point descriptor, because we'll talk a bit more about this. As I mentioned before, this is basically a vector that is encoding the local appearance of a key point, okay? And what we want is those descriptor to be photometrically invariant. So it means that if I want to localize, I want to match point between an image I take now, and if you turn on all the light will be changing. I still want basically those key points to match. And they should be ideally invariant to geometric transformation as well. Like if I want to do matching between widely different viewpoints, I still want those local key points to match, okay? And for a very long time, we were relying on handcrafted features like SIFT, where you take this little patch, you will extract the gradient locally, and you will basically create an histogram of this gradient, and you can consider that this histogram is representative of this local patch somehow. We had some binary strategy that are still in use in SLAM or any real-time system, and a bit more recently, I would say in the past 7 years at least, then we have seen the emergence of tons of learned feature. Here is, for instance, superpoint, where a neural network is directly regressing the 2D key point location as a heat map, and the descriptor for each and every pixel in the image somehow. Okay, and those learned features, they tend to be better and better. At the beginning, they were barely competing with handcrafted feature. Now they are like very interesting thing coming out. That's a very interesting part of the literature. Anyway, so if you're able to match images, and if you're lucky enough, maybe you will be able to have at least 5 key points that are matching. If you have this, then congratulations, you can estimate what we call the essential matrix. So you can basically together estimate the poses between your cameras, and you can reconstruct the 3D structure of the scene by triangulating those points. Okay, so you can do it for 2 images, that's fine. So now you can basically have like a sort of seed map. From 2 images, you will create a tiny map. Of course, it doesn't cover everything, so what you will do next is that you will try to aggregate new images to that. Because you have this tiny 3-point cloud, you can try to localize another camera in this global referential. Okay, and now you know the pose of this camera, so you can basically match points between this new image in your map with the previous images, and you will triangulate new set of points. So your map is going to grow. and then you can aggregate more images to that, and you will end up ideally with basically your entire map. Okay, if you end like adding all the images in your data set. So of course it's a bit more complicated. Okay, you have some refinement going on, etc. But at the end of the day, what you get, this is those kind of 3D representation. And what many students, like they're missing when they start 3D reconstruction is that they only care about the point cloud. They're like, hey, good job, we have the point cloud, that's what we wanted. In reality, like the output of the structure from motion is much richer than just a 3D point cloud. Actually, 3D point cloud is not maybe the most interesting in what we are estimating. So what you end up with is a very complex data structure that will contain indeed the 3D points, but also for each of those 3D points, you can have the list of descriptor that has been used to triangulate this point, okay? So you have like basically, you know how this 3D point looks like somehow from different viewpoints, okay? You will have a visibility list, meaning like what image or seeing this particular 3D point, okay? You will also have like, of course, all your original data, all the images, but you now also have the exact pose where those images have been captured. You also know the characteristic, the geometric characteristic of your cameras. You have the calibration, you know the model of your camera, and you know many other stuffs, okay? You have a co-visibility graph between your images, meaning like what camera is looking at the same place as another, okay? So you see that you have all those information, and in general, when we do visual localization, we take full advantage of that thing, okay? We don't just consider a 3D point cloud, we consider that we have a 3D point cloud that is enriched with descriptors, with many things, okay? So knowing that, we can now move to the simplest and most naive localization technique ever, okay? You will see that's a very stupid one, and we'll discuss about that. So, you know, now that you know that the 3-point cloud can contain some descriptors, and that you can extract descriptor from an image, hey, you're like, hey, I can match my 3D point cloud with my image, okay? And then if I have some 2D, 3D correspondence, look at this, like think of some line in 3D space, and you try to align it to 3D points. You will find that you can align your camera only in one position, and all the degrees of freedom will be locked, okay? So look at this image, that's exactly what is happening here. So it means that the premise is simple, actually. If you can have 2D, 3D correspondence using those descriptor matching, you're done, okay? So, you know, like actually like to estimate the exact pose of this camera, in general, we use what we call like a perspective endpoint algorithm. I'm not gonna go through the details, that's extremely simple. That's actually just an approach. If you give 2D, 3D correspondence, you can get the pose, okay? It's simply solving actually a polynomial system of equation that actually is even simpler because you can rewrite as a third order polynomial form. It will give you a couple of solutions, easy peasy. It's known from the 17th century, probably even long before that, okay? So, you know, well, now we can use that thing. We know to match descriptor, we know how to get the pose. So, you know, we can try this. Imagine you have an image, you have a 3D map, each 3D point has a descriptor, you match those guys, boom, you get that thing, right? So you see that sometimes you have some outliers. That's okay. We can use like some robust technique like ransack. Again, I'm not gonna go through the details, but well, you can end up with basically a nice pose of your camera, okay? So do you think it's gonna work actually if we do that? Huh? Sorry? Oh, not Siri. I say sorry. Siri is buzzing me now. How do I stop Siri? Okay. So, yeah, actually it's working. Even I will tell you it's working extremely well if you do that. Okay? But it will take you a huge computational cost. And we'll see later that that's not the only problem here. There is something that has to do with scale. Like if you work in a small environment, this thing is going to be a killer. It's going to work super well. Okay? Actually, if you have infinite compute, this thing might be actually one of the best ideas, okay? But the thing, it takes a lot of computation, and why? It has to do with the way we're comparing those descriptors. So I will try to give you a very quick overview on descriptor matching. So imagine you have like a query image and a 3D map. You can extract descriptor from your image, and you have those descriptors that are embedded in your 3D map here. So you see that you want to associate those descriptors with the descriptor in the map. So what you can do is like you can take the first descriptor here, and try to compute its distance with all the other descriptor in your 3D map. So for instance, maybe the distance between D1 and D1 prime is 10. And you will do it for all other points in the map, okay? So now the next thing you will do, so here you can consider the one with the shorter distance is the best match, right? In practice, it doesn't work so well. So what we do is we take the top two matching, like 10 and 20 in that case, the smallest one, and we compute the ratio between them. If this ratio is lower than a certain threshold, we're like, hey, come on, that's a bit ambiguous. They look too similar, so I will throw away this match, okay? So this is what we call the ratio test. And then you repeat that operation for everything else. But here, you can quickly realize that you end up with an n-squared problem, okay? This thing is quadratic, and you don't want to be quadratic. So another cool solution will be that you take your descriptor in your 3D map, and you create a KD tree of that, a binary tree, okay? And then if you do that, then you can do some approximate nearest neighbor, and you can apply exactly the same strategy, but now you can use a data structure that is efficient, okay? And this thing will speed up your matching by 100 times at least, okay? When you scale to something big at least, okay? Because now you end up with an n log n problem. Good. You can also use other kind of tricks, like for instance using a dictionary of word, a visual word. We'll come back to that later. I'm not going to talk about this too much. And if you want to go further, because you see so far what we have seen is very handcrafted, right? This is like, hey, we have some rules, we set some random threshold, okay. And you know, it's not working that well actually. That's always a bit tricky. But like more recently, some deep learning based strategy came out and they're very smart, you know? Like take those two images here. And you see, I don't know if you see very well guys, but there are like some orange points here and some blue points here, okay? Then if I ask you as a human, how can you find the correspondences between them? It's easy, right? It's super easy, you know? And then, but the thing is like, because for us, why it is easy is the whole question here, you know? Because like, it's easy because we see the context, we see the relationship between those points. But the algorithm I talked about before, no, that's not what they see. What they see is that, you know? Now try to do the same. Try to match those things with those things. It's going to be a pain. You will probably be wrong sometimes, okay? Because we were losing like any location information where, you know, like we lose all the context, all right? And this is what the author of Superglue figured out. They were like, hey, dude, you know, like they write this in their paper. I think it's very interesting. When asked to match a given ambiguous key point, humans look back and forth at both images. They sift through tentative matching key points, examine each, and look for contextual cues that help disambiguate the true match from other self-similarities. And look, the last one, so this hint at an iterative process that can focus its attention on specific location. And here the main key point is like the attention, again attention is coming back here, you know. Attention is all you need is also true for key point matching, you know. Because at the end of the day, when you human are matching those points, you always consider the context. You always consider relationship between all those points. And this is what they mimicked, and that was very smart, using a graph neural network. And I'm sorry to talk again about graph neural network. You might be so bored of this architecture after so many days. And then they use actually attention graph neural network where they will compute. So you see the input is the visual descriptor for both images and also the location of those key points in the image. You know? And they enhance basically the key point with the positional encodings. And they compute a self-attention for each image individually and a cross-attention. Then basically through message passing, you can enrich those features, okay? And then now you can pass it to what we call a Sinkhorn algorithm. Do you guys know what is the Hungarian algorithm? We have some Hungarians around, don't we? Yeah. Do you know what is the Hungarian algorithm? That's super cool. You need to read about that, man. Like it should be your pride, and that's a very smart strategy to basically solve in an optimal way bipartite graph matching. Okay, and this is what is used here, but the traditional Hungarian algorithm is not differentiable. So it means you cannot train a network through that. So they used instead a differentiable version of that is called Sinkhorn, that will give you basically an optimal assignment between your key point matching. And this thing is extremely good. So if you're interested in key point matching, this one actually is one of the most interesting paper. And now most of the key point matching strategies, they're built upon that foundation. So well, you see we have like fantastic way to basically match key points, match descriptors between the 3D space and the 2D image, all right? They're great. But now the problem is like, and some of them will be faster, some will be slower, whatever. But now, you know, when you move to basically a very large scene, imagine like you have a huge 3D map like this of New York City that will contain like millions and millions of points, okay? So imagine you have millions and millions of descriptors. If you want to localize this query image, imagine you want to know where this particular key point is located in this 3D map. So you will take this path, you will extract some feature out of it, and you will be like, hey, let's compare it against millions and millions of key points. First, it will be slow. Number two is that, oh, maybe this key point is here. Look, here we're looking at a window that if you go in New York City, you have those kind of windows everywhere. So maybe this point is here. Maybe this point is here. Maybe this point is here, or here, or here. And you will end up with potentially like tens of thousands of possible locations for that point. They are too ambiguous, it's too slow, it's not gonna work. Again, if you have infinite compute, hey, you're gonna make it work, right? You can try all possible combinations, you will do it, right? But in general, that's not what we want. We want something effective. And to do that, we perform localization in multiple stages. First, we take our query image and we do what we call a global matching. You remember what I talked about image retrieval? That's what we do here. And we're like, hey, this image has been acquired near this place. So instead of comparing against like all the 3D points of the scene, which will never work, what we do is we just extract a local 3D point here, and we will match, actually, again, a very tiny location. And now you can basically go from coarse to fine. You can estimate the 6 degrees of freedom of your query image in the map. So how this global matching is performed, this is typically image retrieval. So basically the idea is you have a database of image. They can be geolocalized or not, doesn't matter. And you're like, which one is the most similar to me? Okay, so in another word, it's like you have this database of image. You will have some feature extractor. It can be a CNN, it can be whatever you want. And you will basically extract representative global feature for each of them. So I take an image, I put that in my descriptor space. I take the next one, I put this guy in my descriptor space, blah, blah. You will do it for all the image in your database, okay? And you will store that, you know, like in something you can query fast, basically. And then you will do the same for your query image. It will be somewhere in your latent space. And to know which one is the closest, you can look in the latent space, which one is the closest to that, and then you should end up with the most similar image. Easy peasy. So the whole point is how we have those feature extractor here, right? How we learn that. And the traditional technique, like long before deep learning, we basically got inspired again about those NLP people, okay? I'm a bit sour at them because like for a long time, computer vision was considered like the pinnacle of AI. It's not the case anymore. Now we are very inspired by them with the transformer. But back in the day, we were still inspired a bit by what they were doing, you know, and especially with this idea of bag of word. So do you know what bag of word is, by the way? Yeah? Can you tell me what it is? Okay, I cannot hear you, don't worry. It's like, imagine you have a dictionary, okay? Like a normal dictionary, like it's just the list of all the words in your language, in English, whatever, okay? And you take a text and you will basically, every time you see a word, you will do +1 in this word, okay? So you create a histogram of word, and this histogram somehow will be representative of what is inside of your text. So imagine you have a football magazine. What word will come very often? You will have a high frequency of, I don't know, Messi, maybe? He's not in the dictionary, but you will have high frequency of ball, win, I don't know, like, you know, all those things related, run, whatever, okay? If you read at a more like a text about theology, about, you know, you will see God coming up, maybe Jesus, whatever, okay? So you will have different frequencies of words depending on the content that you're reading. So you see that now you can retrieve text. So that's a very old idea in NLP, in natural language processing. But now how do you transpose that to images, you know? Now we want to use what we call visual word, okay? But what is a visual word, right? It doesn't really exist. We don't have a dictionary of pieces of image, right? And then, so what is it? It's basically just a quantized, like this is a database of a quantized visual feature that we extract, okay? So don't worry, we'll come back to that in a minute. Like how we create basically a dictionary of visual word is actually rather simple. So what we do is we take lots of images, tons of them. Like you take 10 millions of images. For each of those images, you will extract some local feature, okay? And you extract some descriptor. It can be whatever you want. Super point. It can be sift. It can be whatever. You extract all those guys. You can, then you have now their representation in the vector space. Okay? And then you cluster those guys with k-min. You say, I want 10,000 clusters. Each of those clusters is considered as one of your words. That's all. Okay? So you have your vocabulary tree. Congratulations. In practice, that's a bit more complex. We do it hierarchically, but I will skip on that. It doesn't matter. So now that you have a dictionary, what you can do is that if you have an image you want to characterize, you can extract key points and you look for each of those key points, their descriptor, to what cluster they belong. And then you create that histogram. And then now you can basically make some localization. Easy, okay? So that's the idea. I will skip this one because we don't have much time. And there were an extension of bag of word that came after that, which is called VLAD, Vector of Locally Aggregated Descriptor. So in the VLAD paper, what the author basically realized is that the fact that you discretize is not always very good. Because imagine like you can have like many words in W1, for instance, associated to that cluster. But you know, if all the points are on this side of this cluster, or if all the points are on the other side, actually they can look widely different because of the quantization error. So the idea of VLAD is instead of just counting things, is that for each word, we will associate a residual vector, okay? You will basically cumulate those vectors here with respect to the center of the cluster, okay? And then you can have a better, I would say, representation, something more expressive somehow, okay? So, of course, the only backside of it, I won't go through too much details, is that you end up with something super massive. You end up with basically one vector per word, okay? That's extremely sparse, and is going to be very huge because k is the number of words you have in your dictionary, and potentially you can have like hundreds of thousands of them, okay? But anyway, that's working pretty well, and those techniques have been used for quite a long time. And in 2014, when, you know, like people talk a lot about that, ImageNet, challenge, and then AlexNet that came up, etc. Then people were like, hey, now we have those fantastic CNN that came out. Why not, instead of using SIFT and all those old school stuff, let's use basically some pre-trained CNN and let's try to do the job. And that's exactly what people have done. And it was not working that great, actually, okay, at the beginning. They came up with a fairly good idea about normalization, but it was not catching up so well against like traditional techniques because those things, they were just trained on ImageNet. It was not fine-tuned for the task here, right? And people had no idea how to do that until NetVLAD came out. And that's a very cool paper that really changed all the game, okay? It got like inspired by VLAD, but tried to replicate every single component of VLAD using basically deep learning. So the first one is, you know, like in the normal pipeline is that you extract some descriptor, right? Here they say, okay, we are not gonna use those old school thing. Boom, a huge CNN is gonna do the job to extract the descriptors. Next is basically, normally what we do is the aggregation, okay? We try to count the number of words, for instance, or we try to create those residual vectors from VLAD. Here they replace it with, like, actually something that is rather complex, I will say, from nowadays standard, to basically have a sort of assignment. And more than this, is that they will learn actually during the training, like the cluster of visual word as well. So very smart, actually, development. So here there are a few equations, but we don't really care. It's just a recap on how bag of word is working. So bag of word is very simple. You basically, for each word in your dictionary, you will look which descriptor belongs to that word. So you see that this operator here is simply, you do +1 if this is closest to the cluster you're looking at, and 0 if not. Okay, you create basically just an histogram. NetVLAD is almost the same, except that now, like if the descriptor belongs to the cluster you're looking at, then you will compute the residual vector that you will add to this word. That's all, okay? So the main problem here is that when people try to mimic that with deep learning, is that this operator here is really not differentiable. Whenever you have something that does 1 or 0, you cannot differentiate that thing. What does it imply? You can do backward propagation, that's not gonna work, right? So what's a very stupid AI people, what are we always doing? We take the soft of that. We take the softmax, always, you know, easy peasy. So you will tell me, hey, not much novelty, right? That's exactly what they do. Now they have a soft assignment. You see, like, you have here on the top the exponential of the distance to all the cluster, to one cluster, and here is basically the normalization you have in softmax. That's all, right? And if you, here you have an hyperparameter, if you put this guy very high, it will look like very much like a hard assignment, basically. So here we can replace this hard assignment by a soft one. Congratulations, you're done. Now you can backpropagate. But NetVlad, they're much smarter than this. They were like, yeah, but you know, like, how do we know the center of those clusters? You know, what we want is to train together a good feature extractor, but we also want to train. We want to embed somehow like those center cluster directly in a neural network during the training. And for this, they simply used another MLP to do the job during the training. Again, I'm not going to go through the details, but that's what it's doing. So together, during the training, you learn good descriptor to extract, and you learn basically some cluster of visual word somehow. Okay, and well, already that's quite complicated, but they were facing even more problem than this. Is that at that time there were no like clear data set to train that thing. So they did something. They took Google Street View time machine. So you know, like you have like Google Street View, and you can go through time as well. Okay, so they took that thing, and so you know they train with triplets of images. You have your query image, and you will have a negative image. Is very simple. You know, you take an image very far away. You know, like in the Google Street View. Imagine like I take a picture in Nepal, and my negative sample can be a picture from Mexico. I know it's going to be negative. It's not the same place. Now, what is more difficult is that the positive sample you're not sure because Google Street View doesn't tell you anything about the orientation. So they had to do some mining. That's actually a quite complex process. And then when you end up with basically one anchor image, your query image, one positive sample and one negative sample, you can do something super fun, is that you can basically use what we call a contrastive learning here, metric loss. Here is actually a triplet loss. So what you want to do is in your latent space, you know, you don't solve a classification problem. You just want to learn the proper feature such that your positive sample will get closer in the latent space, but your negative sample will be basically set far apart from it, okay? And this is a very central method for so many things. And that's exactly what they used back in the day. And so using all those things together, it was very not trivial. And yeah, they did a very good job at it. And okay, without talking too much about the result, that was a huge breakthrough, okay? So here again, it's just for image retrieval. I have a database of image, which one is the closest to the image I captured. And now that you know that, you can combine what we have seen before. You can combine the, like local descriptor matching with image retrieval. Okay, so you can basically extract some feature from your image. You will do some image retrieval to restrict the area you want to search, and then you can do feature matching. And they work so well together. Okay, I will even tell you basically those kind of hybrid strategy, they're the most scalable, and they are for most of the time the most accurate as well in most scenarios. Okay, so here is what we call hierarchical or hybrid, but hierarchical is better, visual localization. And if you don't really know what to use, this thing is always going to work. Is it always the best? Not always. And I would say, you know, here I just presented NetVlad, but there are so many works that are coming like every year, and they're fantastic. And, you know, now just if you use Dino V2 or Dino V3 directly for localization without any fine-tuning, it's already going to be pretty good, honestly, okay? But, you know, like there are still many papers coming up. Now we rely on huge transformers. It's a bit different, right? But anyway, you can have something very accurate. So to come back to hierarchical localization, I told you it's very good, but this is not necessarily the fastest. This is not necessarily the best for privacy preservation, because look, you have all those data, you know, you will need your structure from motion map if you want to do that. So it means that you have all your images stored somewhere. And then for privacy, that's not super good. So anyway, you know, like people were trying to find solution how we can improve that pipeline. Super difficult to be better than this. And in 2015 or so, someone came up with a bit of a crazy idea, very simple idea. It's like, you know what? What if we simply use a basic CNN? This CNN outputs only 6 parameters. This is the pose of the camera. You give me an image as input, I give you the output of the pose, you know, for a given scene. That's all. And the architecture, there is nothing. Now the whole point, so this thing is PoseNet actually, And we can have a look on how this thing is working. That's a very old video. We can move around. But basically, the only input is this image, and it tells you where this camera is located directly. And it takes a couple of milliseconds because the network is very tiny. Okay? So they propose some data set. And back in the day, it was a real revolution. Okay? Even though there is no architecture, there is nothing, it was very, very new. So you might wonder how to train that thing. Okay? So the training requires some image and pose pairs that in general you're going to obtain by structure from motion. But you don't need the 3D structure of the scene. You can throw it away. Okay? So for your training, what you want to do is you want your network to remember the relation between image and pose. Okay? So you will take basically a portion of this image you use for the scene reconstruction as the training set and some over to test how you're going. Okay? And you're simply going to train your network in that way. Okay? Because the ground truth pose for a given scene. Okay, imagine we reconstruct this room in 3D, and then I want to train PoseNet on that. I will just take all the image per pose. I will train my network. And if I want to localize myself now, I take a new image, and I can reuse my network that I've trained before. Okay? So we have 2 regression heads in general, one for translation, one for rotation. And you can basically regress that. You need just to be a bit careful on how you regress your rotation because there are many ways to represent rotations. Some are better than others. Okay? I won't go through the details. Quaternion is a pretty good choice, I would say. Or rotation matrix is doing well. Never use Euler angle, that's all. If you do that, you should be fine. So back in the day, they were using the GoogleNet architecture that now is quite outdated. Back in the day, ResNet was not even existing. And then GoogleNet is an architecture with some early exit for a better flow of the gradient. It's almost like Ensemble in some ways. Anyway, it doesn't matter. So they simply remove the softmax and they replace it with basically some regression. That's all. Okay? So something that was interesting for the time is that they were showing the importance of pre-training. And that was huge back in the day, I would say. Now it's obvious to all of you because we went through all this self-supervised learning, Dino, etc. We know that we need basically a good pre-trained network. Back in the day, it was not that obvious. So it was also a very interesting insight that they were proposing. So as I told you, the output is simply, the translation and rotation as a quaternion. So this is, just a tiny vector here. And they have the beta parameter to balance them. Because this quaternion potentially, the maximum norm of a quaternion is 1, but what is the maximum translation? It depends on the size of your scene. Okay? For instance, in that room, it's going to be 30 meter by 30 meter or something. Okay? So you need to rebalance those losses somehow. Okay? So they use a beta parameter that back in the day was tuned for every scene. So that was a bit of a pain. And they ended up with actually pretty amazing result for the time. But if you were digging a bit into this, you were quickly realizing that this strategy is extremely inaccurate. Okay? It's not working as well as advertised. And then people try to scale it up to bigger scene, and boom, it's not working. It can be because of catastrophic forgetting. It can be anything. Okay? But it's not accurate, whatever you do. It has some advantages as well. For instance, this is actually quite robust. So even in a scene where you don't have much texture, it's doing the job. Okay? And so many follow-up work came out after that. But in general, those direct regression techniques, they are not that accurate. Okay? So here are a few results I can pass. So, some advantages, very fast inference, robust in low texture. You don't need to have this explicit 3D structure. You don't even need the training images. You can throw them away. So you see that your privacy problem is resolved. Okay? So the main problem is that this is not very good. It doesn't scale. It's not accurate. So it doesn't do the job. So people were like, hey, but nonetheless, that's interesting. And then came the scene coordinate regression technique. So it's actually quite similar to what we have seen right before. The only difference is that now so the idea of scene regression, people were like, yeah, we want more geometric insight. Okay? We want those insights to be closer to what we did before in our previous, traditional pipeline. Okay, key point matching, pose estimation, stuff like this. And so they started from the same idea. I give you an image. I have a network, but instead of predicting directly the pose, only 6 parameters or 7 parameters, I will basically try to regress like a tensor with 3 channels inside. And for each pixel, basically what we try to get is the 3D location of this pixel, of the projection of this pixel in the 3D world in the scene coordinate. Okay? And that's the reason why we call them scene coordinate regression. So you see, this 3D point cloud has the specificity that it exists in the frame referential of the scene in which you want to localize. So you can understand that as a point map regression. It's another term that you might have heard of if you work in 3D. It's a one-to-one mapping between the pixel in your image and their corresponding 3D points in the absolute reference of the scene. Okay? And again, here, what does it mean? It means that we have some 2D coordinate and they're mapping in the 3D scene. And we have seen before that if you have this 2D, 3D matching, we're done. You know, the job is done. Look at this. You use your network, you take your image, using your network, you get the 3D position of those points in your map. Look at this, you use RANSAC and PNP, like a perspective endpoint that we have seen before. Boom, you localize yourself, done, right? And then people realize that this thing is actually much better. But how do you train that thing, you know? And the first people trying to do that, it was in 2013. So you see, at this time, neural net was emerging somehow, like people were using other stuffs. And actually what they did is they took a data set where they had some RGBD image. And they simply trained for each image how they can regress the 3D coordinate in the scene, basically, using a random forest. Okay? So was it working? Yes. But this thing was, so to train, you need like RGB, depth, all the pose. So you need so many things. In many situations, you don't have the depth, okay? And especially not the dense depth, right? And it was extremely slow. I mean, this thing, I had to use it at some point because one reviewer asked, hey, why don't you compare against super old technique? Thank you. That's a pain, okay? That's taking forever to basically converge to something. This is, of course, scene specific, like PoseNet that we have seen before, and it doesn't scale at all. So later on, some people were working in Niantic. You know, Niantic is the company basically doing like Pokemon Go and those things, okay? They were like, can we do something better? You know, we don't have this depth to train. And they got another idea. They were like, let's keep that network that can predict. So instead of random forest, let's use neural net first, okay? It's a CNN. And we're gonna regress, basically, like some 3D coordinates, okay? But many of those points at the beginning of the training, they will be useless. They will be bad, okay? So what they basically propose to do is to sample sets of points randomly in that 3D space, okay? And they try to basically estimate the pose and to compute the reprojection error for many candidates, okay? And they use basically another neural network to estimate the quality of basically each hypothesis that you get. And then again, a softmax, and you sample through this softmax to have like the best hypothesis, and then you do back propagation and you train. And if you do that, you don't need any depth, okay? You just hope that at some point the training is gonna converge to something, okay? And this is surprisingly working well. But the main problem of that, so this technique is called DSAC, it takes like more than a day for a tiny scene. So if you want basically to use DSAC to train a localizer in that room, yeah, like good luck with that, it's gonna take you one entire day. So super slow. Much more recently, in 2023, the same author proposed something called ACE. And this thing is super cool. It's called, so it stands for Accelerated Coordinate Encoding. And what they did is like they have trained now a backbone on like so many images. Okay, so this thing is frozen. Okay, and then when they do their training, they do multiple things here. So they take like for each patch you will have one corresponding feature somehow. Okay, and what they do, they shuffle those features. They will mix up all the images together. So all the patches. Okay, and for all the patches, they will try to predict their 3D position using simply a tiny MLP. Okay? And then they only basically guide their training through the reprojection error on the images. Okay? And why do they shuffle here? Is because you want basically to train for each batch on as many possible variety of images as you can. Okay? Because if you train image per image, then the training will be extremely slow. Okay? Because basically you will keep adjusting one with another. Okay? And this shuffling idea is so good actually. Okay? And you see that there are many advantages in what they have proposed. First, you have this thing that basically doesn't need to be retrained, is fixed. And the only thing you train is that given some features, I have a tiny MLP that will regress the position for each point in my image, for each pixel. And it means that when you want to train for one scene, it takes now 5 minutes, okay? And that's a very cool network to play with because it's super fast, okay? So very nice one, and then, yeah, as I told you, like, this is much, much, much faster. Here is ACE, like, it takes a couple of minutes, and here you have DSAC star that we talked about before, 200 minutes, and then you have, like, yeah, over DSAC, it takes forever, okay? So it was a huge, huge progress in those kind of scene coordinate regression techniques. And these days, I can see, like, plenty of new ideas that are emerging. So now, like, how you can train the similar kind of thing, but without using any prior SFM reconstruction, how we can localize using those techniques in large scene, many, many things that are very cool that are emerging. I really like those kind of paper, even though at this point they cannot really compete yet against the hierarchical localization technique we have seen before, you know, image retrieval and pose estimation. So now we will just conclude on that because, like, you might be confused, we have seen so many things, and then, yeah, what to use when. So here is basically a little summary of all of this. So if you use absolute pose regression, okay, like basically PoseNet, again, fast inference, you don't need a 3D map to train, that's super simple to do. You just take any CNN backbone, boom, you're done, okay? But this is not gonna scale, it's gonna be scene specific and not super accurate. Now, scene coordinate regression, they are quite close to absolute pose regression, but they're a bit more accurate. The rest is mostly the same, okay? And finally, hierarchical localization, like amazing accuracy, very good scaling, but then you need to go through this entire SFM reconstruction. You have bad privacy that I forgot to write here. It's memory intensive, et cetera, okay? And there are a few more techniques, but here is, I would say, the main families that you will face, okay? So there are plenty of future directions that you can follow actually in visual localization. I try to just put a few of them, like where the field is going. One of them is, for instance, like some multimodal kind of localization. Here is my work actually published last year, is how we can localize a vehicle using plenty of cameras installed on the car and how we can localize it in a HD map of a city, okay? And that's fun because now you don't work with 3D maps, you don't work with images, this is a graph. And again, here we use some form of graph neural network, we use some scene-coordinate algorithm, those kind of things. Now I can see that the field is moving towards huge pre-trained model like anywhere else, right, obviously, okay? As well, this is like everything now in image retrieval will be something like that. There are many other fun things to do like cross-modal localization. Now, what if what I want to localize instead of a normal image is thermal image? How are you gonna do that, okay? It can be cross-view localization. It can be, so many things like this, like plenty of challenges that are not fully resolved, okay? Like here is a bit extreme, is like how you localize this image into this satellite view, okay? And they look very, very different, okay? So some people also, I was talking about GeoGuessr. Recently, like maybe 6 months ago, like, I wonder if it's Luc Van Gool. I don't remember who published that thing, but they made like basically an AI much better than any GeoGuessr in the world, right? It's super accurate. So yeah, you have plenty of cool challenge you can tackle basically. Something I see a lot, I'm editor in a journal, so I see those papers coming out every day these days, is basically how you can embed some, language model into that as well, okay? Like instead of just giving an image to localize yourself, what about if you localize with text? Okay, I say, I see some people in a room with red chairs and where am I, okay? Those kind of thing. Or like imagine you have like, you're a robot and you can tell the robot, go to the location where there is a fire extinguisher. Okay, how do you do that? How can you localize this basically element in the scene? So you need some form of grounded reconstruction of the scene somehow. Okay, there are also a lot of very cool work. Here is another work that we have done actually with NAMI maybe 2 years ago. Is like the problem is how we localize ourselves in implicit representation, like nerve, Gaussian splat, those kind of things. And many people have been working on that as well recently. That's pretty fun. You also have like some more technical related challenge, how I can make those things work on embedded systems. Like there are all those new very cool data set and new hardware basically for ego localization somehow. Okay, like with those, I don't know, like Google glasses or what is it, like the new glasses from Meta, those kind of thing. Still the challenge of how you scale to a city, it's still something difficult. There is a challenge that I'm working a bit with these days is like how you preserve the privacy when you basically localize yourself. So yeah, there are very fun techniques that have been deployed for that. And then here, just the last slide to conclude. We'll actually be right on time, that's great. Visual localization is a core problem with application in many different fields. And what will come next is basically, yeah, how we scale it, how we make it work with plenty of different kind of data, and many other stuff that will come up. And privacy is one of them that I like, I told you. So I hope it gave you a pretty good overview of this field. And yeah, we still have time for a few questions. So thank you so much.
Yeah, thank you, Francois, for such a wonderful and interesting talk. I must say, I only tried structure for motion like 50 years ago when you were doing a PhD and I was a master's student there. Today's talk was a great refresher for me, and I can see the field has advanced a lot. My one question would be, what would you say has been the major breakthrough in 3D? Is it the speed, accuracy, or robustness of these methods?
So like recently, the very huge breakthrough we have seen, like actually in the past 2 years, that's very recent. We just had our sort of attention is all you need moment recently, is that we see new network emerging, and that we call like point map regression, basically. And this is like you can forget completely about geometry, okay? Like geometry is somehow gone now. They start to be very good with that. You take an image or two images, and it will directly give you basically the structure, the pose, everything, the calibration. You need nothing at this point. Image, result. You have the dense 3D reconstruction. And those methods now, they expand to series of images, and they start to scale very well. So, this is, now you can do very cool things in robotics. You don't need to know anything. You put your image, you get what you want. And that's actually, I think, the biggest breakthrough now. And now people combine those things with Gaussian splat as well. So directly regress Gaussian splatting. So not only you have the 3D structure, not only you have the pose, not only you have the calibration, now you have like a realistic photometric reconstruction as well. So you see, we start really to get to something very tangible, very useful. And yeah, for me, that's the biggest breakthrough. And that's a bit sad because all the theory we knew before is now replaced by a huge transformer. And this is working, right? That's the magic of deep learning, and this is what we have to work with anyway. So that's the path I'm following a little bit these days.
Thank you.
Okay.
Hi. So I have like a few quick questions. So like if you're like combining like SLAM and NERF, are like propagating that rendering loss back to the SLAM in order to like update the poses or not?
Oh, well, okay. So you can refine the pose using NERF eventually. That can be a way. You can even use like some self-calibrated NERF if this is what you mean. I mean, combining NERF and SLAM, to me this is a bit antagonistic because NERF is very slow and SLAM is very fast. That's something I'm always buzzing a bit with because maybe in that case, and I think I told you last time, I think Gaussian splat might be a bit better. And that can be a good combination because you can start with some key point based localization, and then if you have some photometric sort of reconstruction of the scene, implicitly, it can be NERF, it can be Gaussian splat, doesn't matter. Then you can have probably a much finer localization and much more robust to texture-less environment. So that can be a good combination, but people are moving on that already quite fast, I would say. There are like a lot of work in that direction. Old one will be nice slam, and there are many other things popping up actually. Yeah. So yeah, this is something I think people have explored already.
I have like another question. There's like if you are doing like bundle adjustment and like you are detecting the loop and then you are updating the push, then how are you like updating like Gaussian splat, reconstructed map or like not reconstructed map?
Okay, when you do loop closure and then you assume that for each you have like some Gaussian, you have some splats in your map, right? Okay. Here is difficult because you know the splat you have, they won't necessarily correspond to the 3D point you have triangulated, right? Because you know you have this division that you make during the Gaussian splat, and then those things, they're not grounded to the 3D map somehow. So it's not a use case I've seen, but that's a fun thing, I think. Like how you move them accordingly, that's not easy to be frank with you. I don't know even if it's feasible or it will take a lot of resources because one way it will be to refine the entire Gaussian splat, you know, and you can have some rough approximation on how you will move them with the nearest 3D points, I guess, but it's going to be a total mess. It's going to be very computationally expensive to do loop closure in a Gaussian splat environment like this, I think. But that's a challenge. That's a very interesting question.
So like so I think the way is like to like maybe like retrain the Gaussian splat or like.
Yes, you will have to. You will have to do that. There is no way you can skip that thing. Totally.
Thank you for the lecture, sir. My question is regarding how do we localize dynamic systems which are not stationary in elevation axis?
What do you mean by dynamic system exactly?
Just like drones, they are moving, right?
Yeah, you will use the same kind of idea. Like, you know, you take, okay, if you want to be real time, you don't need to localize all the time. Okay, you can say, at time t, I'm located here, right? So maybe you will be a bit late, but in the meantime, you can do some visual odometry in the meantime. You will know how your drone has moved, right? So you can basically take the pose you have located and you can add the visual odometry to that. And then you see, you can have a low frequency localization, okay? And then you can update that using the visual odometry and you can be real time. The way we are gonna do it is that you can use, for instance, for drone, a satellite view is gonna do the job. And you know, you can have the 6 degrees of freedom. So you know exactly the elevation, you know everything, right? So it doesn't matter if it's a drone or a car, it's gonna work for anything. All right, then if we don't have any further questions, thank you again so much. And it will be time for the tea break. Thank you.